And I guess I'm sure you don't care how wacko it's been, but it's yes, sir.
Well, I'm having a question engaged in the software. Do you have anybody in the office who can sit down and give about 10 minutes to let me appreciate the software, what I'm getting into?
Okay. And what regard?
Let's just take a picture of this and that. I'm trying to see where it should appear on the computer and so forth.
Okay. What software are you talking about, though?
Cengage.
Cengage. Okay. The website or the things from this book? The like calchat.com and calview.com.
That stuff. Yes.
That stuff. Okay. Are you trying to get on website? That's the homework package, which I don't use, but make it available to you.
Yes, I'm trying to see what's all available to me. And
Okay.
Some of the things that I get, it's like the wrong answer.
Right.
I want to see what happened.
Okay. All right. Now, for the stuff from the text, like the calchat.com and calview.com and larsoncalculus.com, okay, I think you just type in the website and you go there. Now, how to navigate that, I never have. Have any of you navigated those? Okay, can you maybe get with Bill right after class? Does that work?
Okay, what's your name?
Frederick?
Frederick? Okay, thank you.
Okay. Now, the WebAssign stuff, I've requested the class code, and as far as I know, they haven't sent it yet. Now, I haven't gotten on email the last 2 days because they have been wacko. I'll tell you a little bit of it. I didn't get paid in December. I didn't know that until I got home Friday evening, just after 5, got the mail, checked my bank statement, and I had $330 in my checking account, which is way low. No deposit in December. I went to our website. There was a deposit, okay? A check number, that kind of stuff. And of course, it was after 5. Nobody was on campus any longer. So I called the bank and talked with them. Nothing was received. They guaranteed me nothing was received. So I emailed the school, of course, knowing no one would be able to respond until Tuesday morning. Holiday weekend, of course, that would happen. And a few people did read emails and let me know that nothing would happen until Tuesday. But yesterday I finally got a phone call, and they cut me a check, and it's supposed to be getting here today sometime. But evidently, someone had sent an email to HR director in my name saying, change my routing number. And she forwarded that and had them change my routing number and sent the money somewhere else. Okay. And I would never, ever trust email. I wouldn't put my routing number on email. I don't trust that email can't be hacked or something. So I would never do that. And I've heard since then they put into place 2 new features. One, you can't make any payroll changes except in person. Duh. I never would have done it in the first place except in person. And number 2, they now have something that lets you know if something's coming from external source or internal source. Which if it's that simple, why weren't we doing that all along? I didn't know there was that capability. But anyway, that's my sad story. You heard the violin music in the background, didn't you? It was really bad. All right. Taylor? Yeah. All right. And so I had 2 hours of office hours this morning, the only 2 hours I've had so far this week, because Monday was a big office hour day. And I spent most of the first hour trying to straighten out that mess. And then since then, students who say their attendance hasn't been in or they're not getting it yet. And a student, I don't know why I got an incomplete. Well, you didn't turn in the research paper. Oh, well, yeah, dealing with that. And then get a grade change. And the whole morning's, in 2 hours, I got 1 paper graded. That's all. I have a stack of papers already this early in the term and got 1 paper graded. So that's why I was running sideways. not forward at all. Backwards most of the time. All right, so enough of that. I knew y'all would really appreciate that. Okay, and like I said, I've requested the class be set up and that they give me a code. And like I said, I haven't been on email except just to send something to receive, I haven't been able to check emails since the weekend. So I don't know if they've responded or not. But as soon as I know something, I will let you know what the class code is. I'm not making any assignments on WebAssign, but it does have good tutorial help, or at least I've been told it does. They say they have it. I've been told by students they don't really care for it that much, or they're very slow, but they do have other help that you can certainly use. The author has great help. Now, I don't know how to navigate it, and for instance, his first example we're going to do today, see larsoncalculus.com for an interactive version of this type of an example. And then all of your homework exercises are at calcchat.com. And does this one have CalcView? Yes, this one has CalcChat and CalcView. So he provides those two websites. Absolutely no code required to access those. Anyone can go and get those. So I don't, frankly, see much of a need for the WebAssign, but I provide it, the code, as soon as they get it to me. I'll provide it to you so you can access it if you need to. All right, any questions? Any other questions before we get started today? All right. Now, I'm waiting for the projector to come on. Last time we talked about, just got to say it, about the limit of composite functions. And since we didn't get to do the example, I thought, well, let's review that because I know, a week, oh boy, how much is lost in that. The next theorem greatly expands, this is what we did last time, your ability to evaluate limits because it shows how to analyze the limit of a composite function. Y'all remember what composite functions were? F of g of x. Okay? These are, back in pre-calculus algebra, you probably thought, oh, that's just another thing for them to exercise I have them do. Oh my goodness, whoa, be still my heart. I believe that Gavin is here. Yes. Okay. All right. Anyone else whose name I didn't know? Okay. You probably thought of, oh, this is just something else to make it complicated, functions difficult and complicated and confuses. No. These are incredibly important, okay? In calculus, we will be doing chain rule, composite functions. That's exactly what they're used for. In computer programming, if you're doing some pretty complicated things, but you have repeated things that you'll be calling on the program to do, rather than having it coded in each time, you just name a function, name an operation, name something, and send it there, and it does it. That's basically composite functions as well, okay? So there's lots of very practical applications of this. So here's what we got. If f and g are functions such that the limit as x approaches c of g of x is some value L, and the limit as x approaches L of f of x is f of L, okay, you would expect that, then the limit as x approaches c of f of g of x, that's your composite function. One function operating not on a number or a value or a variable, but on another function, okay? Then the limit of f operating on the function g will be, and here's something you can do if these are functions that all that is true, then you can take the function outside and say it's the function of the limit of x approaches c of g of x, which we know to be L, so this would be f of L. A lot of blah, blah, blah with letters. Let's actually do an application of it. The example 4, if I can get my string unstuck here. Okay. And this is the one I said, see larsoncalculus.com for an interactive version of this type of an example. Okay. So here's the first one. The limit as x approaches 0 of square root of x squared plus 4. Now, what would be your approach to that limit? Plug it in, and guess what? It doesn't look any different from any other limit that we would have done. What would that be? 2, okay? Let me get my pen set up, sorry. Okay, this would be the limit as x approaches 0 of the square root of 4, right? Because when you put in a 0 for x, it's going to 0, and, well, let's just call it the square root of 4, which is 2. Okay. Now, did you even notice there was a composite function there? There is. The innermost function, the g of x, is g of x is equal to s squared plus 4, and the outer function, the f function, is the square root function. So that is a composite function. But look, all you do is plug it into the g and then evaluate the f. That's exactly what we did. We plugged x into the g and got 4, and then took the square root of 4 and got 2. Ha! And you didn't even know you were doing a composite, did you? Let's do the next one. What would be your approach here? Plug it in. So what would this be? The cube root of? Second? 8, okay, because you got 3 squared is 9, times 2 is 18, minus 10 is 8. And anyone know what that is? 2. All right, done. Okay? Didn't even probably realize the inner function here, the g of x, is your 2x squared minus 10. Plug the 3 in that, and you get 8. The outer function, f, is a cube root function. Cube root of 8. Yeah, you really had to spend a lot of energy. Aren't you glad you had to read that theorem? All those letters and all those numbers. It's that simple. Sorry. I wish I could make it harder, but I can't figure out how to do so. All right. Any questions? Okay. Let's see how they do it. I'm sure it's going to be very complex. Because, okay, they do a little bit. Because the limit, they take the innermost function first. The limit is x approaches 0 of this. Plug in a 0 for the x. You get 4. And the limit of the square root function, which is your f function, as x approaches 4, because that's your L here. And as x approaches L of square root of x is square root of 4. Okay. A lot longer roundabout way to do it. Just plug it in. Same thing with, you can conclude then that the limit of the whole thing is 2. Yeah, I'm glad they added that. All right. The b part, again, they take the innermost part, the g function, as x approaches 3 of this would be 2 times 3 squared minus that's 8, and then take the outer function, the limit as x approaches 8, the cube root of x is cube root of 8, which is 2. And then I'm sure they have a conclusion here. Yes, you can conclude that that's the answer. Okay, we did it, and we saw it was the answer, and then you can conclude that's the answer. Good. All right, you got it down? Those are all the steps you have to go through every time, right? Yeah, okay. Now, the limits of many algebraic functions can be evaluated by direct substitution. The 6 basic trigonometric functions also exhibit this desirable quantity, but what do you have to keep in mind about those 6 basic trigonometric functions? Are they continuous everywhere? 2 are. Which 2? Sine and cosine, continuous everywhere. Everywhere imaginable. The others, however, do have discontinuities. Where? Tangent and secant. Discontinuous where?
Everywhere except for whenever there's where it crosses 0.
Okay, where the, okay. I think we're getting right to it. Let me mark the roll before I forget. This will be, is it Frank?
Yes, sir.
Okay. I feel like this is Okay. You're saying where something is zero. Well, for tangent and secant, okay, it's sine over cosine is tangent, 1 over cosine is secant. So where anywhere cosine is 0, tangent and secant not defined. And where is cosine 0? Don't think so. The origin is 1. Sine is 0 at the origin. Whereas cosine 0. Second? Basically. Second? Yes, all your half pies. Pi has, 3 has pies, 5 has pies, 7 has pies, negative half pi, negative 3 has pies. All your half pies, cosine is 0, so therefore your tangent and your secant undefined there, okay? And secant and, cosecant and cotangent, where would they be undefined? Oh, I got to check with some of your trig instructors. I'll have some serious talk with that guy. Well, that was me. Okay. Where is sine 0? All your pies, your whole pies. 0, pi, 2 pi, 3 pi, negative, yeah. At your whole pies, that's where sine is 0, and therefore since cotangent, cosine over sine, and cosecant, 1 over sine, those would be undefined there. Okay, so, just a little bit of trig reminder. Okay, so let's look at this. Limit of trigonometric functions, let C be a real number in the domain of the given trig functions. Wasn't that a little weasel word to get them out of having to worry about it? Because if it's not defined, it's not in the domain. So that's what we're excluding then. So as long as C is in the domain, the limit is x approaches C of sine C is, guess what? Sine x is sine C. Cosine, cosine C. Tangent x, tangent C. Wow, this is incredible. Cotangent x, cotangent C. Wow, never would have seen that coming, would you? You just plug it in, plug it in. As long as you're in the domain. As that C is in the domain, meaning not one of the values. Sine and cosine, good anywhere. But tangent and secant, not at your half pies, and secant, cotangent, cosecant, not at the whole pies. I like whole pies better than half pies anyway. Never mind. Okay. So let's do one. Oh boy, I hate it when they do this. Okay. What is the limit of tangent x is x approaches 0? Say again? Someone said it. Yeah, 0. Okay, because tangent of 0 is 0. Because it's sine over cosine, and sine of 0 is 0. Boy, I'm glad they gave us such a challenge there. Okay, how about this one? The limit, oh, what in the world do we do with that? As x approaches pi of x cosine x. Say again? It's pi. Is that what you said? Yeah, because it's pi. Oh, plug in pi is what you said, okay? When you plug in pi, what do you get?
Pi times the cosine of pi.
What's the cosine of pi?
Negative 1.
-1. So this will be? Negative pi. Perfect. There it is. All right, you're reading my short one. Never mind. Okay. All right. Everybody see that? Plug in, and this is a product, so you can split that up as the limit of a product of two functions is the product of the limit of those two functions. And this is pi, and this is limit is x approaching pi of cosine x would be -1, so that makes it negative pi. Okay. Good deal. Let's see if there's a C. Yes, there is. What would this one be? Limit as x approaches 0 of sine squared x. Anybody? 0, because sine of 0 is 0, and sine, and now, I'm not exactly sure why they wrote it this way, But this and this mean exactly the same thing. As long as you have the sign X in parentheses, this and this mean the same thing. This is, to me, a shorter hand of doing it, and that's how I'm used to seeing. But either way, plug an X in here, sine of 0 is 0, 0 squared is 0. Sure enough. Composite function with trig. This is a product with trig. That's just a trig function. So that's a composite function. The sine function, and then you square it with the squaring function. Let's see if there's a D. No, there's not. Good. I don't have to jump up again. All right. Any questions on those? So, what's our strategy for finding limits? Okay. You studied several types of functions whose limits can be evaluated by direct substitution. Okay. This knowledge, together with the next theorem, can be used to develop a strategy for finding limits. So here's what I have. Functions that agree at all but one point. Okay? So let's let C be a real number, any old real number. Let f of x equal g of x for all the x's not equal to C. Every other x they're equal in some open interval containing C. Okay? C somewhere in the middle of that. If the limit of g of x, that's the second one there, approaches as x approaches C exists, then the limit of f of x also exists, and those will be the same. So if these two are equal functions everywhere except C, and C and g has a limit as x approaches C, then f also has to have that limit, even though it doesn't have that value. Okay? It will have the limit. So that says that the limit is f of x. If this is true, then even though it's not true at C, but everywhere else it is, that the limit as x approaches C of f of x is equal to the limit of f of x approaches C of g of x. Okay? Because if the only place they disagree is at C, let's say f is coming in like this and has a hole there, or jumps up here, down here, up here, somewhere else at C, and then continues like this, and G does the same thing, but is exactly equal to that, but it has a value at C. Okay? Okay? Now, but F has a different value there, then if the limit is x approaches G is there, then the same limit would be for F. Doesn't have to be that value, but the limit would be the same. We did that before, I think, with open circles, and we saw that. So this is just saying the same thing. So here, well, find the limit. Uh-oh. What would be your first approach? Plug it in, plug it in. What do you get? 0 over 0. Now, if that was 7 over 0, stop right there, because the limit will never, ever, ever exist. Okay? But this is 0 over 0. That's what I call an indeterminate form. Okay? So, can't tell. Okay? Certainly, the limit of this function exists, and that function exists, but the limit of this is 0, so therefore we can't tell if this is going to have a limit or not, unless we do what? Factor. Oh, what a wonderful word. Okay? Can we factor that numerator? Is what? X? A little louder? I can't hear it. X. Okay. You say x squared? Okay. What's next? Okay. Let me show you how I do sum or difference of two perfect cubes. You probably have done this before, but here's my little way of doing it. First, take the cube root of both numbers and keep the sign. That'll be x minus 1. Okay? First factor. Okay. Second factor. Now, this is my rule. Okay? But it works. Either sum or difference of two perfect cubes. Forget about the original problem. Square the first one here. What does that give you? X squared. Then opposite the product of the two. What's the product of those two? negative x. Opposite of that is positive x. And then square the last one. And what do you get? Plus 1. Okay? That is the factorization. It works for sum or difference of two perfect cubes. Take the cube roots of both, keeping the sign in between, and then do that little rule. Square the first, opposite the product, and square the last. Okay? Works every time. Take that and divide it by x minus 1, and what happens? The x minus 1s divide out. Now you take the limit of this, because those two are the same, right? So take the limit as x approaches 1 of what's left of this g of x. And what you get?
Plus x plus 1.
Second?
X squared plus x plus 1.
Yes, x squared plus x plus 1. Take the limit as x approaches 1. Is what? 3. Perfect. All right. Now, even though this is not defined at x equal 1, it's defined everywhere else. Okay? But because this is equal to that everywhere except x equal 1, then the limit of that is good everywhere. Everywhere, even at x equal 1. So therefore, by our last theorem, if that has a limit of this and they're equal everywhere except at 1, then the limit of the original function is also 3. Okay? Now, hopefully they'll draw a graph of it. I don't know if they will or not. They do in the book, in the text. Let's see if they do on the slide set. Let's see how they do it. Okay, let f of x equal that. Good. By factoring and dividing out common factors, just like we did, we rewrite f as that. Everywhere except x equal 1, because it's not, the original wasn't defined there, but g of x is defined at x equal 1. It has a value there. So for all x values other than x equal 1, that parabola that we had, this one right here, is that. Okay? X equal 1, it can't have a value because that makes sure the denominator is 0. So we put a hole there, hole in the graph to x equal 1 and y is equal to 3, or f of x, f of 1 equal 3, because g doesn't have a hole there. So since this has a limit of 3, this has a limit of 3. Coming from right or left, the limit is still 3. F and g agree at all but one point, and therefore if g has a limit, f has the same limit. Even though it's not defined there, it has a limit there. Make sense? All right. That's sort of a nice thing about limits. Even when something's not defined, you may still have a limiting value there. And this one does. All right. Now, this is a little bit of a side note here, but every time you do factor a sum or difference of two perfect cubes, the second factor is always going to be a quadratic. That quadratic is never factorable any further. Unless maybe you can take out a common factor, but you should do that at the very beginning. But once you do that, that's never factorable. In other words, it's not factorable. It could have a root. This one has no roots. But that is never factorable. Try factor to your heart content. You're not going to get that to factor. I was going to say that's why it has no roots here, but just because it's not factorable doesn't mean it could have irrational roots. This one doesn't have any roots. That's why it's all up there. Okay. So the only real root to our original function was that one, but we won't go there yet. Okay. Now, that was example 6. Oh, here's a solution. Okay. Because the limit as x approaches 1 of g of x does exist, by plugging in, you plug it in and you find out, and because that does, and g of x is equal to f of x everywhere except at x equal 1, then you know that f also has a limit at x equal 1. Same limit as g of x, which is 3. Okay, are they going to say it again? All right, this is good. I thought they just did this, okay? Was I asleep at the wheel? Okay. the limit as x approaches 1 of that is indeed 1 squared plus 1, which is 3. All right. We did a while back. Any questions on that? That was example 6. Okay? Now that says we're finding a strategy now. Learn to recognize which limits can be evaluated by direct substitution. How do you do that? Plug it in and see if they can be evaluated with direct substitution. Okay? When the limit, and what are the places that you can't? Anything to give you a 0 in the denominator, can't do that. Or negative under a square root, can't do that, or even any even root. Or negative or 0 in a log, can't do that. Those are the main ones. When the limit of f of x approaches c cannot be evaluated by direct substitution, try to find the function g that agrees with L for all other values other than x equals c, chooses g such that the limit of g of x can be evaluated by direct substitution, then apply that theorem, conclude analytically that then f of x, the limit of f of x as x approaches c, has to be the same as g of x. If they're equal everywhere except c, that's going to be true. It's going to be g of c. Now, the whole question, that sounds really good with words. The question is, how do you find that? And that's what I remember Bill right at the beginning said, do it analytically. And that's what we did and we'll continue to do. Now, the other strategy, use a graph or table to reinforce your conclusion. Frankly, I do that if I have a graphing calculator handy, because I don't like having to graph things too badly. Okay, but if a graphing calculator will do it fairly quickly, yeah, I'll use that. All right. So we're going to look at some of these techniques. We just did the dividing out technique. One procedure for finding the limit analytically is dividing out, which we just did. That involves dividing out common factors, which means you have to factor what you can, and then, if possible, divide out common factors. Cleverly named dividing out technique. Okay, so let's try this one. Find the limit as x approaches negative 3 of x squared plus x minus 6 divided by x plus 3. What would you try first? Good old blade. Plug it in, plug it in. What would guess give you? 9 minus 3 is? 6 minus 6? 0. Now, if everything else would be fine, your limit's going to be 0. Until you do the denominator, and you find out that's 0 also. No, we don't know. Can determine it, we do not know. So, what would be your technique? Factor. Good deal. And how do we factor that numerator? The denominator can't be factored. It's prime.
X minus 2 times x plus 3.
X minus 2 times x plus 3. We sure hope the x plus 3 would be there, but y'all can do your factoring right. That divides away, divide it out, and what do you have left? The limit of this now, I should keep forgetting to give myself room, as x approaches negative 3 of x minus 2 would be negative 5. Perfect, perfect, perfect. Okay. Let's see how they did it. Any questions on that before we look at theirs? Okay. See how they did it? Although you are taking the limit of a rational function, you cannot apply that because the denominator is 0. Well, the denominator being 0 has you do two things. The first thing, take the limit of the numerator as well. If that was anything other than 0, stop right there and say does not exist. The limit cannot exist. But if that numerator is 0 and you have 0 over 0, then you pursue this. Okay? And we found out they were 0 over 0, so direct substitution fails. All right? Because the limit of the numerator is also 0, blah, blah, blah. And they say because the limit of that is also 0, the numerator and the denominator have a common factor of x plus 3. Yeah, I guess you can conclude that. So what you do is factor that numerator. Sure enough, you get x plus 3 times x minus 2. That's now your g of x. X can't equal negative 3 because it can't over here, so it can't over there either. But it can for x, g of x. So you now evaluate the limit of g of x as x approaches minus 3. Boy, they can take it long enough to do it. And that gives us negative 5. Perfect. Any questions? All right. The result is shown graphically. And frankly, when you look at this first one, you don't immediately see that's going to be linear until you do the dividing out. And then you say, oh, yeah, that's x minus 2. That's going to be a line of slope 1 and intercept negative 2. And slope 1 is going to pass through all these points. And at negative 3, you have a hole in the graph. Okay? From the first one. The second one, when you did it, the g of x wouldn't have a hole in the graph because that was just x minus 2. But the first one wouldn't have it because you can't have x equal to negative 3. Any questions? Yeah, I always want a graph. Yeah, right. Okay. But it's good to see. So if you have your calculator, graphing calculator, suck it to it. So in that example, direct substitution produced a meaningless fraction form of 0 over 0. They say it's meaningless. It's not meaningless. It's just indeterminate. Now, if that was 7 over 0, I love 7, you can tell, or anything pi over 0, or anything over 0 other than 0, hang it up, no solution. But if it's 0 over 0, we don't know. It may have no solution, or it may have a solution. Indeterminate. Okay? So you have to investigate further. When you try to evaluate a limit and counter that form, remember you must rewrite the fraction so that the new denominator does not have 0 as a limit. So, dividing out common factors, if that's an option for you, do it. Okay? Do it. Now, that was page 67, example 7. And by the way, I forgot to say, example 7 also is clarsoncalculus.com for an interactive version of that type of example. Okay. So let's now move to rationalizing technique. Oh, y'all are good at rationalizing, aren't you? Oh, no, I really didn't mean that. No, that's not the kind we're talking about. Talk about this one. Another way of finding a limit analytically is rationalizing technique, which involves rationalizing either the numerator or the denominator. Now, back when we were dealing with radical expressions, we never wanted to have a radical in the denominator, so we always rationalize the denominator. Now we're going to rationalize wherever we want to. Whatever is giving us the problem, we want to deal with rationalizing that. We know that rationalizing the numerator or denominator means multiplying the numerator and denominator by the conjugate. Now remember what the conjugate is? They're always binomials, okay? A rational part, an irrational part, a real part, an imaginary part, A plus B, A minus B. Whatever they are, a conjugate keeps the first term, changes the sign of the second term. Always binomials. So here we have, for instance, to rationalize the numerator of this one, which if you're trying to evaluate it, you never would want to do this. Because if you knew what x was and it was something not 0, okay, then you would do that. Okay. In fact, I'm not even sure why they're showing you this one, except just to rationalize the numerator. If you had a limit of this, if the limit was 0, it's going to give you no solution, ever. So you wouldn't even bother rationalizing. If it was any other x other than 0, no sweat. Plug it in, plug it in. So this is not one that you would do calculating a limit. They're just showing you to rationalize the numerator. Okay. Well, you multiply by the conjugate. What's the conjugate of this? The square root of x minus 4. Okay? So you multiply numerator and denominator by that. Why do you have to multiply both? What is square root of x minus 4 over square root of x minus 4? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value at all. Okay? So that's what you would do, multiply numerator and denominator by x, square root of x, minus 4. And why you would do that, I'm not sure. But that's how you would rationalize that. Now, this one does make sense. Okay? What would be your first step? Plug it in, plug it in. What happens if you plug in a 0 here? 0 plus 1 is? Square root of 1 is? Minus 1 is? 0. And plug in a 0 down there, you get 0. Now, if this had been a negative 3 over 0, stop right there, no solution. But this is a 0 over 0, so we must continue. And what would we continue doing? I'm not going to try to factor that. No factors involved. But what can we do? Multiply by, I'm going to put parentheses around this, is what? And what is that? The square root of x plus 1 plus 1, okay? But if you multiply the numerator by that, you've got to be democratic about it and multiply the denominator too. X plus 1, square root of x plus 1 plus 1, because that's 1, okay? Now, yeah, we may have simplified the numerator, but we sure have screwed up the denominator, didn't we? What does the numerator become then? What do you get when you multiply a minus b times a plus b? A squared minus b squared. Well, your a here is square root of x plus 1. So when you square that, what do you get? X plus 1. Okay, there's the first part. And then the b part here is 1. Okay, and you do minus 1 squared is minus 1. All right. And I think I can add that. Those add to 0. Okay? In the denominator, it's a mess. But I wouldn't multiply the mess. I just write them as factors. X times the square root of x plus 1 plus 1. And now what do you notice you can do? You wind up dividing out anyway. This x will divide out that x. Guess what? You just got rid of your problem child, right? Oh, I mean, okay. Okay, so what do we have now? We have in the numerator 1. And the denominator, the square root of x plus 1 plus 1. And we take the limit of that as x approaches 0. And guess what? Don't know if we can do it or not. That numerator is sure not going to be a 0. That's going to be a 1. But what does that denominator become? Anybody? Second? 2. So the limit is 1/2. Oh, we saw that coming, didn't we? Okay. Does that make sense? Okay. So, if you have an indeterminate form, not factorable, but it has especially a radical in it or something else that's going to be messy either in the numerator or denominator, and that's going to be a 0 that's going to be a problem, then try rationalizing whichever you're rationalizing, numerator or denominator. In this case it's numerator. Multiply by the conjugate over itself, so you're multiplying by 1. Do the math, see what you get. In this case, we just turned out with x. And in the denominator, we had x times whatever we multiplied by. The x's divide out, still was dividing out, and you had that. Any questions? Let me erase this. Any questions? All right. And let's see how they do it. By direct substitution, you get indeterminate form, so you must proceed elsewise. So, the limit is x approaches 0. They show you got an indeterminate form. They already said that, but now they're showing you, indeed, you do have it, okay? I'm glad they amplified that, okay? In this case, you can rewrite the fraction by rationalizing the numerator, which is multiplying numerator and denominator by the square root of x. Plus 1, so you must multiply numerator and denominator by that. Well, you're multiplying by 1, not changing the value, just changing how it looks. And when you do that, you get x plus 1. When you square a square root, you get what's under there, minus 1. That's your second part of it. And then you had x times square root of x plus 1 plus 1. That gives you x over that. The x's divide out. Now, I know y'all are at calculus level and you wouldn't do this, but I've taught Math 100 enough to know that sometimes students, when they do this, they'll make that numerator 0 because they got rid of it, right? No, it's not a 0. X will go into x one time. Okay, 1 over 1. So you don't even have to write it. So it's 1 over that. This we can take a limit of. That's for poor English. The limit of the first, since that is the same as the second, except to x equals 0, we can take the limit of the second one there, and we find out that's the limit of 1 over 1 plus 1, which is 1 over 2, 1/2. So, even though the first is not defined at x equals 0, it still has a limit at x equals 0, and that would be 1/2. Make sense? Now, I'm not about to want to graph this, but let's see if they graph it. Oh, they do, don't they? Okay. Now, don't know if you recall that this is what this would look like. I sure wouldn't. But this is basically what your square root function looks like. It's sort of upside down and shifted 1 to the left and all that, and raised 1, all that kind of stuff. But at x equals 0, not defined. But at all other values, it is defined, and the limit is at 1/2. I'll let them do the graphing. I mean, I love graphing, but okay, never mind. So, I think they do a little bit more, yes. Or you can do it with a table, is what they called it. In other words, numerically, like we did to begin with, let x get closer and closer to 0 from the left and from the right. Oh boy, remember how much fun these were? This is getting closer and closer to 0.5. This one's getting closer and closer to 0.5. So sure, we feel like that's 0.5 or 1/2. So, why give us all the analytic techniques if you're going to go back and do this again? But this should show you that still works. It does still work. Any questions? Now here's one other technique. Not my favorite, but certainly one that is indeed true. It's called the squeeze theorem. I've either read or maybe even taught from books that call it the sandwich theorem. So whether you like squeezes or sandwiches, I sort of prefer sandwiches. Squeezes are fun, but you know they don't fill my stomach. Okay. The next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. Now the other, remember, with the f and the g were the same functions except at one thing, so they were the same coming in and going out. These are not the same, except in the limit that they have the same value at the point in question. So if g of x is this one, and h of x is this one, and f of x is always in between g of x and h of x everywhere except possibly there. Okay? Well, it has to be there too, but it can be the same value. And even though f may not have a limit here, if g does and h does, and they're the same limit, then f has to have the same limit as well. If it's always in between those two functions. Well, that's a pretty big order to fill, making sure that it's always true. But here's what it is. Right. H of x is always less than or equal to, it's fine for it to be equal to, f could have touched there, this can't be greater than, okay? And f of x is always less than or equal to g of x, so you could have touched there, you know, whatever, that's fine too. But never that f would be greater than g of x. But if it's always in between those two, and the limit for these two both exist at some fixed value, then f has to have that same limit. It sort of makes sense. It would have to be that way. If that's true, the top is always true, and the limit's the same, yeah, they got to have the same limit. So here's how they actually state it. If h of x is always less than or equal to f of x, and f of x is always less than or equal to g of x, for x in an open interval containing the value c, except possibly at c itself, it may be that f is not defined there, or whatever. And if the limit is x approaches c of h of x is L, and that happens also to be the limit of g of x as x approaches c, they're definitely not going to be the same values anywhere else, but x equals c, if they have the same limit, and that's L, then automatically L has to have that same limit. Okay. All right. The squeeze theorem, also called the sandwich theorem, there, I said it again. And I don't like this one, the pinching theorem. Okay, I guess that's fine too. I've never had a book named it that before. Two special trigonometric limits here. This is another theorem. And this is one they'll prove using the squeeze theorem. And this is important. It will be important later, and you'll see it. The limit as x approaches 0 of sine x over x. Okay? Well, if you plugged it in, what would you get? 0 over 0. Okay? Now, what's the limit of that? That's indeterminate. And guess what? There's no factoring you can do, no rationalizing you can do. You're going to have to come down to the squeeze theorem to give us that. Here's the second one, the limit of 1 minus cosine x over x. Okay? Well, what's 1 minus, if you plug them in, what will you get? Zero over 0 again. Okay. Well, the theorem says these both have limits. The first one is 1, and the second one is 0. Now, they're going to show a squeeze theorem how you apply this. But here's the way I think of this, okay? And maybe just my weird thinking. But if you picture how, believe it or not, I'm going to say graph. The graph of a sine function looks, remember it's like this everywhere, right? And at 0, it's almost the identity function. And this is the identity function. Well, that's right close to 0. They're on top of each other. They're almost the same thing, so they're 1. Okay? That's how I think of it. Okay? Now, 1 minus cosine x. Well, cosine x at 0 is 1. 1 minus cosine x. Well, very close here. The difference between 1 and cosine x is very close to 0, but this is still your identity function down here. So this wins. This is 0. And the sine function, they both look like that. They look like they're on top of each other, and close to 0, they are very close to being on top of each other. So that's basically an identity itself. The same value of the same value is 1. This is going to 0 fast. This is not going to 0 fast. That's going to be 0. 0 wins there. Okay. Now that's my weird way of looking at it. Now, here is example 9. Well, they're getting all these, aren't they? Good deal. Find the limit as x approaches 0 of tangent x over x. Ooh. Ooh. How can we do that? Any ideas? Stretch the imagination. Those people who were in my trig class had better come up with this one. What was our first technique? Second? Okay, so, yeah. By all means, let's always start with substitution. I forgot that. What do you get when you substitute? Second? Okay, yeah, you're doing my second question. First question, she's doing the second. Tangent x as x approaches 0 is 0, and x as x approaches 0 is 0, so that 0 is 0 indeterminate. Now I like your idea. Since we can't do the indeterminate form, we're going, now we can't divide out, but we can factor. Okay, so let's factor. Well, it's not quite a factoring, it's rewriting. So this will be the limit, I'm going to write it this time, I keep forgetting to, as x approaches 0, of sine x over cosine x over x. Okay? Now I'm going to rewrite that slightly. This isn't quite the same as what we were doing before, but rewrite is fine as long as you do it correctly. Okay? I'm going to put the sine x over x. Okay? And I'll put this as 1 over cosine x. Is that legal in most states? Yes. Okay? Everybody see that? Now, why did I do that? Yes. Okay. We know the limit. The limit of a product is the product of the limits. So that will be the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. Okay? Now, for those people who always like to cancel, which most math instructors say, no, you're dividing out. You remember that? Or y'all don't, they don't say that anymore. Back when I was growing up, they hated you to use the word cancel. And here's one reason. If you cancel this out, that would be sin, but no, we aren't doing that. No. What is the limit as x approaches 0 of sine x over x? One, right? Right down there, we did it. Okay? So this will be 1. And then what's the limit of 1 over cosine x as x approaches 0? How would we do that? Plug it in. And what do you get when you plug it in? Okay. Second? I heard a couple of different answers. 1. Perfect. Because cosine of 0 is 1. 1 over 1 is 1. And 1 times 1 is 1. Okay. I think we're convinced it's 1. Okay. Can't tell looking at that. But again, now I'm going to do it again because I do have room to do it here. How does the graph, can't believe I'm doing this, of tangent look? Okay, at minus pi halves, it's undefined. At positive pi halves, it's undefined. At minus pi fourths, it's minus 1. At positive pi fourths, it's plus 1. So it does something like this. Well, I missed the 0. Okay. Ugh. Look at that. What do you have there? Almost the identity function, isn't it? Right close to the origin that is the identity function. And that is a line y is equal to x, too. So you have close to 0, as x approaches 0, it's that over that, okay, which is 1. Same quantity over itself. Okay, so sure enough, that makes sense. In my mind, in my sick little way of thinking. All right. Does that make any sense to y'all? Okay. So, you can't always go by those kind of gut feelings, but it worked here. Okay. Direct substitution yields the indeterminate form 0, 0. Yeah, we figured that out. To solve this problem, you rewrite the tangent x, thank you very much, as sine x over cosine x, but then rearrange those factors so that the sine x is over the x and the 1 over cosine x is by itself. Now that's a limit of a product, and we can make that the product of the limit. The limit as x approaches 0 of sine x over x is 1, which we saw from the previous theorem, and the limit of 1 over cosine x, just by direct substitution, is 1. So our limit is 1. Okay, it took them long enough to get there, but it's 1. Does that make sense? Yeah or nay? Okay. Oh, and here's a graph. I'm so glad they did this, okay? That is the graph. If you had your graphing calculator and did this, you would see it looks something like that. Now, as long as you somehow avoided x equals 0, it would look like that, okay? And, but if you tried to get it to evaluate at x equals 0, it's going to go haywire because it can't do it. But, sure enough, that's approaching. All right, good deal. Any questions? And if you think about this too, the tangent function, like I said, does like this, and the identity function does like this. They're both negative over here. They would be positive up here. They're both positive over here. So they'll be positive over there. And they both are on top of each other, real close to 1 right there. And in fact, look how close it is. Now, of course, don't even mess with near minus pi halves and pi halves because the tangent's not defined there. Then you have an undefined over a value. That's going to be undefined. Okay. So, not out there, but near 0, yeah, we can still define it. All right. Whoa, me. Shame on them. They left off example 10. How are we doing on time, folks? I can't believe I haven't even gotten my watch out yet. What do we go to? Yeah, so we got plenty of time. Okay. So let's do it here. Example 10. Find the limit of, as x equals 0, of sine of 4x over x. Doesn't quite fit what we had before, does it? Sine x over x, yeah, we know what that one. Sine 4x, we don't know. Do we? Now, anyone have an idea how we could proceed? I'll look in the book real quickly and see what they do. Second? Okay, can I take it out? Yeah, if we were dating, I probably would, but I don't think I will. No. Can't factor it out, no. But you're on the right idea. Rather than taking it out, put it in. Oh, okay, you want to plug in? Is that what you're saying? Or plug in the 4? Wait, what are you asking? Say.
I was guessing.
Okay, yeah. Let's plug it in and see what happens. Sine of 4 times 0 is 0, sine of 0 is 0, and this is 0. So plugging in gives you indeterminate form. Okay. She was thinking beyond that, what do you do next? Rather, you can't factor it out because that's not really a factor there. But, say again?
Would you have like the sine of x over x and then take out, I mean not take out, but the 4x would be the limit of x approaches 0 of 4x?
Right. Okay, I think you're really close. You may be there, but I'm just not quite hearing it.
Okay, you got sine of x over x.
Yeah, we know what that one is.
The limit of x approaches 0 of sine of x over x. Then you have the limit of the x approaches 0 of 4x.
Okay, no, okay.
No?
Not quite. But you're also close. Anyone think of anything to do? You don't take out the 4. We'll multiply, but you can't just multiply randomly by 4 because you change the value. But if you multiply by what? 4 over 4 would work, wouldn't it? So multiply the numerator by 4 and the denominator by 4. Isn't that legal in most states? Okay. Now, what do you notice you have now? We'll be doing this later. I hope you see it's okay now. What if that 4x wasn't really 4x? What if it was, say, u? Wouldn't that be 4 times sine u over u? wouldn't it? And what's the limit? As x is approaching 0, if u, okay, here's the trick I'm doing. Let u equal 4x. That's what I'm doing here. Then as x is approaching 0, u is approaching 0. So this will be the limit as u approaches 0 of 4 times sine u over u. And guess what that is? Remember, you can take the 4 outside. Now, that 4 you can take out, okay? Right? Okay, so that would be 4 times the limit of u, as u approaches 0, of sine u over u. And what is that? 4! Yes, yes, yes. Now, it looks like it was the same thing if we had just taken the 4 out and then you'd have that. But that's not legal, okay? This is legal, okay? And you don't have to change a u. If you can see that sine 4x over 4x, that's sine of an entity over itself. The limit of that is 1. Now you got 4 times 1. Does that make sense? All right. Trick, but if a trick works often enough, call it a method. And now it's a method. Okay. And that basically the same thing they did. Okay. I just wondered if they had a slightly different bend to it, but they don't. That finishes 1.3, which means you can now do some homework exercises. Do any of the odds 5 through 21. They're all at calcchat.com, 7's at calcview.com. Then do either 23 or 25 or both. They're both at calcchat, 25's at calcview. Do any of the odds 27 to 35. They're all at calcchat, 29's at calcview. Do either 37 or 39. They're both at calcchat, 39's at calcview. Do any of the odds 41 to 45. They're all at calcchat, 43's at calcview. Do any of the odds 47 to 61. They're all at calcchat, 53's at calcview. Do any of the odds 63 to 73. They're all at calcchat, 65's at calcview. Do any of the odds 75 to 81. They're all at calcchat, 75's at calcview. Do any of the odds 83 to 89. They're all at calcchat, 83's at calcview. Then try to do number 91 and either 93 or 95. You can explore doing 97 if you would like, and you can look at 99 if you would like. This is started on page 71 and 72, then continuing on 73. There's a 101 that you can look at, sort of an applied problem there. And based on that, you can do 103 as well. Okay? Then you could try to do 105, find functions that would make whatever they ask for there. And then they have some proofs. If you're really into proofs, any of you pure math majors are wanting to be. If you are, the proofs probably are good things to start getting used to, because you will be doing a bit of that. You were a math major. Did y'all do plenty of proofs?
Yes.
I thought so. Okay. Ad nauseum, huh? Okay. So if you are going pure math, then I would definitely take a look at any of the odds, 107 through 111. They should be at CalcChat. I don't know. I haven't looked to see. And then 113, you can think about doing that one if you'd like. There's a true-false, several of them, 115 to 119. I'm not going to ask you many of those type things on a test, but they are good things to think about. Yes? When we finish this chapter 1, okay? And we're making good progress, by the way. 121 is another proof. 123 is graphical reasoning. Finally, we're at the end. So that went through page 73, those who were asking. All right. How are we doing? Oh, plenty of time. So let's move on to all right. 1.4. And you're asking when the test is. See, we just got 1.4 and 1.5 to go. So we made pretty good progress through 1.3. Let's see if 1.4 will be as agreeable. All right. Still in chapter 1. Let me get the slideshow set up first. Still in chapter 1, limits and their properties. And 1.4 is continuity and one-sided limits. Okay? Now, continuity is a big term in mathematics and really a big concept in just about anything. The engineers are just going to usually assume it and fly from there, but it is important to know. So we're going to do a few definitions and descriptions of continuity. And then we're going to look at some one-sided limits, which you might say, what good are they? Well, there are certain applications that it would be. In my pre-calculus class the other day, we had just looking at domains of a function, and if the function was the volume of a sphere, the volume of a sphere is 4/3 pi cubed, and we were talking about what's the domain of that. Well, usually cubic functions, like most polynomial functions, the domain would be all real numbers. But if you're talking about a volume of a sphere, when's the last time you had a sphere, a ball, that had a negative radius? Can you think of one? I can't. How about a zero radius? Oh, there it is. Okay, no, don't have a ball there either. So you can't have a sphere unless you have a positive radius. So there, our domain was only positive numbers, so therefore it could have a one-sided limit because there aren't any numbers over there. So there are times when it may make sense to talk about a one-sided limit. Okay? So first we'll do objectives here, determine continuity. First we've got to define what we're talking about there. At a point, and continuity on an open interval. We'll determine one-sided limits and continuity on a closed interval. And we'll use properties of continuity. We're going to be all over continuity, aren't we? And we'll understand and use the intermediate value theorem. You will. Okay. Let's move on. Continuity at a point on an open interval. Now, y'all know what we mean by open intervals, right? Any interval that's between two values, but they may not include the two values. That's an open interval. A closed interval, it would include the endpoints. And you could have closed on one end and open on the other, or whatever. So we're going to look at continuity at a point and on an open interval. Okay. In mathematics, the term continuous has much the same meaning as it has in everyday language. It's sort of good. A lot of things, there's distinctions there. Informally, to say that a function is continuous at x equals c means there's no interruption in the graph at x equals c, f at c, okay? In other words, if you're going along with the graph, c's over here, it just continues with the value right there. That's continuous. Now, we just saw some examples where at c, there's a hole there. That's not continuous, because a hole is not continuous, okay? Later we'll see some, and we've seen some already, not today, but before, where they are discontinuous there. You know, they have two different values. So it's continuous if there's no interruption at C. That is, the graph is unbroken at C, no holes, and no jumps, no gaps, nothing like that. Okay? That's visually what we mean by continuous. Okay? Now, this figure shows three different graphs. Here is an open interval. Notice it's open because it's not defined at A or at B, but it's defined everywhere in between, except that C is that continuous. No, you have a hole there. If you're driving along here, you fall into the hole. Okay, so you don't do it. Okay. Now, here is an open interval, not counting A or B, and it's defined everywhere. This one wasn't defined there. This one's defined everywhere, but the definition here is not the same as it would be there if that were defined there. So that is not continuous. Obviously, there's a break there. Now here's one that's defined everywhere. on the open interval from A to B is defined here, here, here. So it's defined everywhere, unlike this one. This one was not even defined at C. So this one is defined at C, but it's not where you would expect it to be. So you run into a hole there, a pothole right there. You don't want to hit it, okay? You don't want to go down way down here and then go back up there. That is not continuous, okay? So if alpha C is not defined, obviously the function is not continuous at x equals C. If the limit doesn't exist, then it's not continuous as x approaches C. And if the limit does exist, but it's not equal to what alpha C is, it's still not continuous. Okay? This not defined here, that's defined there, discontinuous there, that's defined at C, but not equal to alpha C. Okay. So, 3 cases of discontinuity. That figure, it appears that x equals C can be destroyed, continuity can be destroyed by any one of the following conditions. Function not defined at x equals C can't be continuous there. The limit does not exist at x equals C. Well, it can't be continuous there. The limit does exist there, but it's not equal to alpha C, so that's still not continuous. Okay, even though the limit does exist, it's not the same as alpha of C. If none of the 3 conditions is true, the function is called to be, this is a weird way of saying it. If none of these are true, okay, then the function is said to be continuous in C. Okay, so rather than being a double negative, here's what it would be. Continuity at a point. Here's a definition. A function is continuous at C when these 3 conditions are met. Alpha C has to be defined, the limit as x approaches C of alpha of x must exist, and it's a combination of these 2, the limit of alpha of x at x equals C, which exists, has to equal the same value of alpha C. Okay? So those have to be true. Alpha C is defined, the limit of alpha of x as x approaches C is defined, and that would be alpha C. So, continuity on an open interval, a function is continuous on an open interval A to B, which is what we're looking at, when the function is continuous at every point in that open interval. Okay? Function that is continuous on the entire real number line is said to be everywhere continuous. Now, I meant to say this earlier, and we're already off of that, but remember when we were doing the squeeze theorem? Okay. That was also on an open interval. Somewhere outside that interval, things could go haywire. We're not worried about that. If it's true on the open interval, then that limit exists if that C is over there. Now, same thing here. If this function on the open interval, everything's true, it's continuous on the open interval. It may have all sorts of weird things like this. Remember our tangent function, not defined at negative pi halves or pi halves. So as long as you don't include that, so you could be from open interval negative pi halves to pi halves, continuous everywhere on that open interval. You just can't go from negative 3/4 pi to 1/4 pi. No, that's not going to work as a discontinuity. So you may have a discontinuous function, but if you limit your interval to where it's not discontinuous, then it's continuous, obviously. Okay. So consider open interval I that contains some real number C. If a function f is defined on I, except possibly at C, and f is not continuous at C, then f is said to have a discontinuity there. Thought we'd already said that, but yeah, reminding them. Discontinuities fall into 2 categories. Some are removable and some are non-removable. Okay, that covers everything, doesn't it? Either you can remove them or you can't. A discontinuity at C is called removable when f can be made continuous by just redefining f at C. Rather than being down here, put it back up here where it belongs. Okay, that's a removable discontinuity. discontinuity like this, like the tangent function goes to positive infinity here, negative infinity there, ain't no way you can redefine that and have them be continuous. Okay, so those are your two basic categories. For instance, the function shown here, okay, this one, would you guess that would be, it is discontinuous, it's not defined at alpha c. Is it removed? Sure, redefine alpha c to be that value right there. Whatever that is, define that, that's removed. Okay, that would be redefined? No, okay, narrow the twain to me. You know, this will never equal that, okay? There's no way you can do it. That's a non-removable discontinuity. Is that one removable? Yeah, this is a redefine. This one wasn't even defined, so you just define it there. This one, redefine it from being this value to being that value. And then you remove it. So those are examples of removable discontinuities. And you might think to yourself, so? And I sort of think the same thing. So? Okay. So let's discuss the continuity of each of these functions. What do you think about f of x equal 1 over x? Is it continuous everywhere? No. Where is it discontinuous? At x equals 0. So can we remove that or not? What's your guess? You can remove it? How? Okay, and I can't believe I'm saying this. Picture the graph. At all negative values for x, f of x is also negative. So it's down here in the third quadrant, right? Going to negative infinity. The closer you get to 0, closer it gets there. But for positive x's, where are you? Positive in the first quadrant. Closer you get to 0, you're going to positive infinity. Any way you're going to get those two to meet? No. Okay, how about g of x? Is that discontinuous? Or is it, I guess we always say continuous everywhere. Discontinuous at x equal 1. Not defined at x equal 1, is it? So it can't be continuous. Okay? But that's one of those indeterminates for you. See the first one up there at 0? Undefined. Not indeterminate. Undefined. That's 1 over 0. Always undefined. This one is indeterminate at x equal 1. That's the only place we have a problem. Everywhere else we're fine. We're hunky-dory. Okay? But at x equal 1 we're not. But is there any way we can remove it? You seen something like that before? Yeah. Factor it. And yeah. And you can get a limit. You can find the limit. And since the limit exists, you can redefine it to be, what would that limit be? That would be x plus 1 times x minus 1, right? Over x minus 1 to x minus 1. Divide out. And then you have x plus 1. You're interested at x equal 1. Well, 1 plus 1 is 2. So redefine that to be 2 at x equal negative 1. At x equal 1, you're in good shape. All right. Now, h. It has a special name called the piecewise defined function. Well, that's a polynomial, and hopefully you know this from your pre-calculus algebra. Polynomials defined everywhere. Continuous everywhere. Okay? Okay? And that's a polynomial function, continuous everywhere. However, the only possible problem here would be where? At x equals 0, because that's the place. These are all the x is less than 0, and these are all the x is more than 0. This one includes 0. So let's see what happens with x equals 0. Each piece is going to be continuous everywhere in its piece. But what happens with x equals 0? One. Hey, no sweat there. That's going to be continuous everywhere. It won't be smooth, but it will be continuous. Polynomials are smooth and continuous, but this won't be smooth. That'll be a linear function on the left and a quadratic on the right. So at that place, yeah, it's going to have problems there, but it will be continuous. How about D? What you think? Continuous everywhere. So H and D and C and D are both continuous everywhere. C isn't smooth everywhere, but it's continuous. D is smooth and continuous everywhere. B is not continuous everywhere. X equal 1 is the place it's not, but it's removable. But A, discontinuous and no way to make it continuous. It's not a removable discontinuity. Okay, let's see how they answer. Domain of F on the A part is, the domain of F is all non-zero real numbers. So the theorem says you conclude that F is continuous at every value in its domain. Well, that's true. This is a little bizarre to have a theorem right in the middle of a problem, okay? Oh, it's just referring back to this theorem. From theorem 1.3, you can conclude that F is continuous everywhere at every x value in its domain, which is true, okay? It's just that at the place where it's not continuous is not, okay. Why did they put this in here? Okay. Limits of polynomial and rational functions. If P is a polynomial function, C is a real number, then polynomials, this is always true. We know that. It's way back there at 1.3. Okay? Rational function, if it's a rational function, then it's P of X over Q of X. C is a real number, then Q of C is not equal to 0, then that's true. Yeah, I agree with that. Everywhere where Q is not equal to 0. But if C were 0, then this doesn't apply. So there must be something on the next page. Let's see. X equals 0. Yeah, okay, fine. I don't know why they threw all that other in there. X equals 0. F has a non-removable discontinuity as shown here. So all that other stuff was saying pretty much clear is this is continuous everywhere on this part of its domain. This is continuous everywhere on that part of its domain. But at x equals 0, discontinuous and non-removable, which is exactly what we said. They sure had a long way to get around to say that. Okay? In other words, there's no way to define f of 0 to make it continuous. Yes, that's what we said. None whatsoever. Okay? The B part, the domain, is all real numbers except x equal 1. You can conclude that G of continuous at every x value in its domain. Yeah, we got that. Has a removable discontinuity because you can divide out the problem factor, which is x equal 1, divided out by factoring the numerator, dividing out the x minus 1s, and then you still have a hole there, but it's removable because you can plug the hole with f of 1 or G of 1 equal 2. It'll work. By defining G of 1 as 2, the redefined function is continuous for all real numbers. Okay. The domain of H, this is the third one, is all real numbers. The function H is continuous on minus infinity to 0 because that's the linear part. It was because h of x, and at 0 to infinity, that's the quadratic part, but because they have a common value at x equals 0 of 1, then it's continuous everywhere. Not smooth, but continuous. Here's the linear part, and that doesn't include 0. No, I'm sorry, it did include 0. The quadratic part did not include 0, but even if you put a 0 in there, you have the same value. So it is continuous everywhere. It's just not smooth there. You have a jump there. Not a jump. An angle there. Let's put it that way. Not smooth, but continuous. Now, why am I bringing up the smooth part? Guess what we're going to be doing the rest of Calculus 1? Taking derivatives. Okay? Now, you probably don't know what those are yet, or you might. But if you do, this is differentiable everywhere. This is differentiable everywhere, but the derivatives are not the same. That's why it's not smooth. Okay. Don't worry about that now. That's a preview of what you're paying for. The D part, the domain of Y is all real numbers. Glad they put this in here. And because C is any real number, sine of C, sine limit x approaching C of sine of x is sine of C. And because sine is defined for all real numbers, then any real number C you put in there will work. Wouldn't be true for 3, 4, 5, 6, but it is for 1 and 2. So I'm glad they put that one back in too. Yeah, right. Okay. And that's what the sine looks like. It's a periodic function, meaning it continues looking like this in both directions ad infinitum, forever. So over the entire domain, it's continuous. Make sense? Tangent, secant, cosecant, cotangent? No. They have discontinuities every about pi apart for all of them. Okay. So they're only continuous over their domains. The domain is all real numbers. All right. How are we doing? Oh, no, it's almost time. So sad. Okay, we're at the top of page 76 is where we'll be getting next time. And let me put a mark there. And let's see if we got far enough to have any homework exercises here. We hope so. Yeah, that's right. I think you could do any of the odds, 5 through 9. They're all at Calc Chat. 5's at Calc View. Okay, no, stop there because the rest of them are one-sided limits. Okay, we didn't quite get that far. Good deal. Any questions? All right. Seems so strange, first time I've seen you this week, to say, have a good weekend, okay? But have one anyway, okay? Strange or not.